So today we'll take up the 34th session on relative velocity. In this we'll discuss mm, the relative velocity two-dimensional collision problems. Okay, that will be discussed in two phases, phase 1 and phase 2. I'll write it down. Okay, first what we'll discuss in today's video. I'll state it first. Okay, so we'll discuss relative velocity collision problems in two-dimensional. Two-dimensional relative velocity collision problems. Relative velocity, two-dimensional relative velocity collision problems. Fine. So this will be discussed in two phases, phase 1 and phase 2. Discussed in two phases, phase 1 and phase 2. Discussed in two phases, phase 1 and phase 2. Fine. Phase 1 and phase 2. In two phases we will discuss it. Phase 1 and phase 2. Alright. First we'll take up the problems from phase 1, then we'll take up the problem of phase 2. So in phase 1, it will be assumed that the relative acceleration between the two colliding bodies is 0. Relative acceleration between the two moving points is 0. This we'll discuss in phase 1. Alright. Then we'll take up the problems on phase 2. In phase 2, it will just be the reverse of phase 1. In phase 2, we will assume that the relative acceleration between the two colliding particles is non-zero. That will be discussed in phase 2. So, relative acceleration will be denoted in short by A relative. So, in phase 1, it will be assumed that A relative is 0 throughout the instant of observation, starting from initial moment till the point of collision, till the instant of collision. In phase 2, it will just be the reverse of it. A relative is non-zero. So in phase 1, A relative will be 0. In phase 2, A relative will be non-zero. First, we will take up the problems on phase 1. Then we will pass over to the problems on phase 2. Alright. So I'll write it. Alright. Fine. So first, we will discuss phase 1. First, we will make a small theoretical discussion on phase 1. Okay. So phase 1. Phase 1. Alright. So take this problem, understand it. Suppose F is the frame of observation. Alright. P1 and P2 are two moving points. This is the situation at t बराबर t1. At time t1, p1 is moving with some velocity u1f with respect to f, and p2 is moving at some velocity u2f with respect to f at time instant t बराबर t1. This is the initial time instant. All right. This is the initial time instant. At t बराबर t1, p1 is having a velocity u1f with respect to f, and p2 is moving having a velocity of u2f with respect to f at initial instant t बराबर t1. Now what happens? They move in some arbitrary way and they collide here at t बराबर t2 say. So t बराबर t2, but this is the collision point where two points collide. This is the instant of collision. T2 is the instant of collision. T2 is the instant of collision. So, see, in phase 1 we have assumed that relative acceleration between the two colliding particles is 0 in the entire time interval t1 to t2. First, for the sake of argument, let us assume that general case that nothing has been said about a relative. All right. Now, as seen from frame F, displacement of P1 is this much, d1f, and displacement of P2 with respect to F is this much, d2f. So d1f and d2f are the respective displacements of points P1 and P2 with respect to frame F in the time interval t1 to t2. One more thing, displacement of P2 with respect to P1 in frame F will be this one. This is the displacement, relative displacement of P2 with respect to P1 in frame F in time interval t1 comma t2. So dp2 p1 is the displacement of p2 with respect to p1 in frame F in time interval t1 to t2. So displacement of p2 with respect to p1 is simply this much. Okay. Till here in phase 1 nothing has been said regarding a relative. All right. For the time being, assume that a relative is non-zero. Okay. So this is the trajectory of P1 with respect to F in T1 to T2. This is the trajectory of P2 with respect to F in T1 to T2. This is the displacement of P2 with respect to P1 in frame F this much in the time interval T1 to T2. As seen from P1, trajectory of P2 is something like this. This curve is the trajectory of P2 with respect to P1 in time T1 to T2. Trajectory of P2 with respect to P1 in T1 to T2. Alright. Till here we have assumed that nothing has been said regarding a relative. General case it is non-zero. Okay. So displacement of P2 with respect to P1 is this much, and this is the relative trajectory of P2 with respect to P1 in time T1 to T2. Now if we make another additional restriction, let a relative be 0 for all t belonging to T1 comma T2. What is this a relative? Relative acceleration of point P2 with respect to point P1 in frame F. Let this be 0 for all time instant in the time interval T1 to T2. This will imply that the relative velocity between P2 and P1 in frame F that will be constant for all t belonging to t1 comma t2. This will mean that the relative velocity of p2 with respect to p1 in frame f is constant, and that is just equal to the relative velocity at time 0, which is denoted by u relative, that is just u2f minus u1f. One more thing, relative velocity constant implies motion along straight line with constant speed. This I hope is clear. Relative velocity means motion of point along straight line with constant speed. So relative velocity constant meaning path of p2 with respect to p1 is also a straight line. This curve again merges with this straight line. Is it clear? So see, before assuming a relative, general case we assume that a relative was non-zero, and this was the relative path of p2 with respect to p1. But if we impose the additional restriction that the relative acceleration between p2 and p1 in frame f in t1 to t2 is 0 throughout, that means two things. First thing, relative velocity of p2 with respect to p1 in frame f is constant. That is same as the relative velocity at time t1, that is u relative, u2f minus u1f. And secondly, relative acceleration of p2 with respect to p1 in frame f is 0, meaning path of p2 with respect to p1 also becomes a straight path. That is, this trajectory coincides with this straight line. Is it clear? So we'll say that in time interval t1 to t2, p1 will observe that p2 is moving along a straight path at a constant velocity this much directed towards p1. This is what p1 is going to observe. So p1 will observe that in time interval t1 to t2, p2 is moving along a straight line directed towards p1 at a constant velocity of u relative. Is it clear? So after applying this restriction, in time t1 to t2, in time interval t1 to t2, p1 will observe that p2 moves in a straight path directed towards p1 at a constant relative velocity of u relative. p2 moves along a straight line towards p1 at a constant relative velocity of u relative. Here it is u relative, it has become slightly congested. This is u relative, alright. This is the final conclusion. Here u relative is the relative velocity between the 2 points at the time instant t barabar t1, that is at the start of this time interval. So finally we will say this much. Initially p1 p2 are having velocities u1f and u2f with respect to frame f. Then at time t1 p1 is here, p2 is here. They, as seen from frame f, they move along some path and come here. This is the point of collision at t barabar t2. So as seen from frame f, in the time interval t1 to t2, p1 will move along this arbitrary path and come here. Similarly, as seen from frame f, in the time interval t1 to t2, p2 will move along this curve and come here and then collide at t barabar t2. Then I said displacement of p2 with respect to p1 in frame f in time t1 to t2 is simply the straight line vector, shortest straight line vector from p2 to p1. That is the relative displacement of p2 with respect to p1. Then I said, in general case, path of p2 with respect to p1 will also be some arbitrary curve. Then I said that now we apply additional restriction that throughout the time interval t1 to t2, relative acceleration of p2 with respect to p1 in frame f is what? 0. That is, relative acceleration of p2 with respect to p1 in frame f is 0 throughout this time interval. That meaning relative velocity of p2 with respect to p1 in frame f is constant for all time belonging to this time interval. and this constant relative velocity will be equal to u relative, that is the relative velocity between 2 points in frame f at time t barabar what? t1, that is u2f minus u1f. So here we are assuming that we are observing p2 from p1. Also relative velocity constant will imply that path of p2 with respect to p1 will also be a straight line path, that is this curved path will coincide with this straight line vector. So in this case finally p1 will observe that p2 is moving in a straight path directed towards p1 at a constant relative velocity of u relative u2f minus u1f, that is the relative velocity between 2 points at t barabar t1. Alright, so this is the final conclusion which I have stated here very clearly. Here it has become slightly clumsy, but this means u relative. Alright, I am repeating it. Okay. So finally we will say that in time interval t1 to t2, p1 will observe that p2 is moving in a straight path directed towards p1 at a constant relative velocity of u relative, that is u2f minus u1f, that is relative velocity between p2 and p1 in frame f at t barabar t1, that is at the start of this time interval. Alright, this is the final conclusion. Alright, so I'll rub it now. So finally the situation is this. In the time interval t1 to t2, t1 is the start of this time interval, t2 is the end of this time interval. At t barabar t1, p1 is here. At t barabar t1, p2 is here. This is at t barabar t1. This is at t barabar t1. At t barabar t1, the vertical separation between these 2 points is y1. Horizontal separation between these 2 points is x1. These are the vertical and horizontal separation between these 2 points at time t barabar t1. Also in this time interval a relative is 0 throughout, as I said just now before rubbing it. A relative is 0 throughout this time interval and they are colliding at t barabar t2. So in time interval t1 to t2 relative acceleration is 0. So in time t1 to t2, p1 will observe that p2 is moving in a straight path directed towards p1 at a constant relative velocity of u relative, that is u2f minus u1f. So u relative also coincides in this direction. So u relative is the relative velocity of p2 with respect to p1 in frame f at t barabar t1, and that is also the constant relative velocity at all time instants of this interval. This angle is theta. So it is seen from this right angle triangle that tan theta is equal to y1 by x1 from this triangle trigonometric. Tan theta is equal to y1 by what? x1. Also u relative direction of u relative coincides with this straight line vector as discussed just now. U relative will have 2 components, a component along x axis, horizontal component u relative x. It will also have a vertical component u relative y. This is theta, this is also equal to theta, this is right angle. So tan theta is equal to u relative y by u relative x. U relative y is the y component of u relative. U relative x is the x component of u relative. So tan theta from geometry is also equal to u relative y by u relative x. From these two equations it follows that these two are equal. So y1 by x1 equal to u relative y by u relative x. So y1 by x1 is equal to u relative y by u relative x. These are the components of relative velocities at t bravo what? T1, that is at the start of this time interval, and these are the vertical and horizontal separations at t bravo T1, that is at the start of this time interval. This is going to be our working formula. This formula is generally very much applicable for projectile motion. What we have discussed in phase 1 is generally very useful in case of projectile motion, meaning two projectiles being fired in air and they subsequently collide somewhere. Both the projectiles will have same acceleration g, downward direction. Air relative will become 0, and if they collide, then this entire theory becomes applicable in that case. Alright, this is the phase 1. Alright, keeping in view the projectile motion, this formula is going to be very much useful. Okay, now in phase 1 we will again subdivide it into two cases, phase A and phase B. Phase A and phase B. Phase 1 will be subdivided into phase A and phase B. In phase A, we will assume that the two particles are projected simultaneously and they subsequently collide. In phase A, it will assume simultaneous projection. Simultaneous projection. And phase B will assume non-simultaneous projection. Non-simultaneous projection. Phase A will assume simultaneous projection. In phase B will assume non-simultaneous projection. Non-simultaneous projection meaning what? The projectiles are not fired at the same instant but at different instants. And simultaneous projection meaning what? The two projectiles are fired at the same instant in Earth's uniform gravitational field. Okay, so phase A and phase B. So this video, 34th video, will be taking up phase A of this phase 1, phase A, and next video will take up phase B. Fine. Now I'll wrap this. Alright, so we'll take up a problem on phase A of phase 1. Fine. So in this video, I'll take a problem on phase A of phase 1. So I'll write down the problem. Two shells S1 and S2 are fired simultaneously. In Earth's uniform gravitational field. From the top of two vertical towers. T1 and T2 as shown. I'll just draw the diagram. Okay, I'm just seeing the data. I don't remember the data. That's why I'm using this sheet. This is the diagram. See. This is the diagram. This is the ground level. These are the two towers. Tower T1, tower T2. Horizontal separation between these two towers is L. Height of vertical tower T1 is 10 meter. height of vertical tower T2 is 30 meter. A shell S1 is fired from here, rightward, at a speed of 20 meter per second, and shell S2 is fired from here at a speed of 20 root 2 meter per second at an angle of 45 degree. This is a situation at t barabar 0, say. Now it is given that the two shells subsequently collide in air. So these two shells subsequently collide in air. And the question is, find the value of L. Value of L has to be determined. Also, it is being assumed that while the shells are traveling in air, only gravitational force acts on the two shells. We have to ignore the buoyancy of air. We have to ignore the resistance on the shells due to air. We have to ignore the effects of Earth's rotation. Nothing. Only gravitational force acting on the two shells. That is, we'll assume that the accelerations of two shells are constant g in downward direction. Fine. So now in this way you can see that this problem is definitely the case of phase A of phase 1. Now they are fired simultaneously at the same instant. That is time instant t barabar 0, let it equal to t1 say. They collide in mid-air at say barabar t barabar t2. They collide in air at t barabar what? t2. They collide in air at t barabar t2. At t barabar t2 they collide in mid-air. Now see, in the entire interval t1 to t2, acceleration of both the shells is how much? as1g, capital G meaning ground frame, that is same as as2g, that is also ground frame, that is g in downward direction, constant. That meaning relative acceleration between these two shells is 0. Now we can observe S2 from S1 or we can observe S1 from S2. So we will observe S2 from S1. Alright. So this means as2 S1g is 0. That is, the relative acceleration of S2 with respect to S1 in ground frame is 0 for all t belonging t1 comma t2. That meaning relative velocity between these two shells is constant for all time interval t belonging to t1 comma t2. That is same as the relative velocity between the two shells in ground frame at t barabar t1, that is initially. That is just equal to u2g minus u1g. This is u1g, this is u2g. Now again they collide at t barabar t2. So in relative velocity constant, implying that with respect to S1, S2 will move in a straight path, and because they collide, the straight path should be directed towards S1. So in time t1 to t2, S1 will observe that S2 moves in a straight path directed towards S1 at a constant relative velocity of this much. So the formula which we have derived just now, y1 by x1 equal to u relative y by u relative x, that is going to be applicable in this case. Fine. Now I'll rub it, alright. So now we apply that formula which we have derived just now. y1 by x1 equal to u relative y by u relative x. All these quantities are at t barabar t1, that is at the start of this time interval, in this case at just time 0. So what is y1? Vertical separation between these two shells at time barabar t1 barabar 0. This is just 10, this is 30. So y1 will be, this is 30, this is 10, so y1 will be this much. 30 minus 10, that is equal to how much? 20 meter. How much will x1 be? x1 is the horizontal separation between the two shells at t barabar t1, which is simply L. This is L, which we have to find out. Now we have to find u relative y and u relative x. What is u relative y? Vertical component of relative velocity of s2 with respect to s1 at t barabar t1. Now for that, and this is the x component of relative velocity at t barabar t1. For that we have to first determine u relative. So u relative, as we have just now stated, this is just the relative velocity of s2 with respect to s1 in ground frame, which is simply u2g minus u1g, which is simply u2g plus reverse of u1g. Now see, this is u2g, s2 I'll draw here, this is u2g, 20 root 2, u1g is rightward 20, so reverse of u1g will be 20 left. So u relative is the vector sum of these two. U relative x is the x component of these two, sum of x components of these two, and u relative y is the y component, that is sum of y components of these two. So u relative x is the x component of u relative, that is the x component of vector sum of these two, which is just the sum of x components of these two. X, this is just along x axis 20, and x component is this much, this is 45 degree. X component of this will be 20 root 2 cos 45 degree. Cos 45 degree is 1 by root 2. This gust comes out to be 40 meter per second. Now we have to determine u relative y. U relative y is the y component of u relative. That is the y component of sum of y components of these two. Y component of this will be 0 because this is along x axis, plus y component of this much, 20 root 2 sine 45 degree, and that is 1 by root 2. That is also 20 meter per second. Now we substitute all these formulas in this equation. Y1 as we have determined is just how much? 20. X1 is L. U relative y by u relative x. U relative y is how much? 20. U relative x is how much? 40. So on solving this, 20 cancels out. L is just equal to 40 meter. This is the required answer. Fine. So here we have discussed phase A of phase 1. So in the 34th session, we have discussed phase A of what? Phase 1. Alright. So in the next 35th session, we will take up phase B of phase 1. Okay. So next video will be continuation of this video. Fine. So I hope it is clear. I fully explained it. If you go through it carefully, it will be clear to you. Fine. So I stop the session here. All right.